All right, so today we're going to finish Chapter 9. Our last section in Chapter 9, 9.10, is Taylor and Maclaurin series. We've talked about Taylor and Maclaurin polynomials, and we've talked about power series, and this section kind of merges those two ideas together. So last time, we focused on using the geometric series to find power series. We ended with using this along with derivatives and antiderivatives. Here we will look at a general process for finding the power series of a function. Okay, and what we're about to look at is going to look very familiar. So this is Theorem 922, and it's the form of a convergent power series. Right, so if F is represented by a power series, f of x equals the summation of a sub n times x minus c to the n. And we're just going to leave the limits of integration, or not limits of integration, but the limits of the summation off, because they can be any, they're going to go to infinity, but it doesn't matter where they necessarily start. So this is our power series for all x in an open interval I. Containing C. Then a sub n is the nth root. I didn't read, I said root. The nth derivative is what I meant to say. The nth derivative at c over n factorial. And f of x equals that value at f of c plus f prime at c times x minus c, f double prime of c times x minus c squared, and it continues forever to infinity. What's it look like? Yeah, it looks like the Taylor polynomial, except that it's infinite, right? Yeah, it's the same thing. And while I'm not going to write it down, you can imagine that if you had this c equals 0, it would look just like our Maclaurin one, right? Yeah, same thing. So this is our form that we're going to be finding, and we're going to be trying to condense things and making them look like what we were seeing at the end of the pieces in the last section. I'm going to shrink this and put one more definition on the same page because it makes sense for them to all show up together here. Okay, so our definition, based on what we just said, actually, is if a function has derivatives of all order, and that means that you can take as many derivatives as you want, right? It never stops. Like polynomials don't fit this description because eventually you take the derivatives and they zero out, and they're zero forevermore after that. So that's not what we're talking about. We're talking about things like trig and exponentials, like the transcendental kind of functions that we were looking at before, that kind of functions. So derivatives of all order at x equals c, then the summation from n equals 0 to infinity of the nth derivative at c over n factorial times x minus c to the n. And it's the same expression that I just wrote out above, is f of c, except for with the a sub n put in. So f of c plus f prime of c times x minus c plus f double prime of c over 2 factorial times x minus c squared. And it continues. This is called the Taylor series for f of x centered at c. And if c equals 0, like we just mentioned, the series is simply called, how it is, the Maclaurin series of f. So Taylor series for f of x centered at c, and then we have our Maclaurin series for f of x, for f. Where's that n pulled from? Up there.
Where did that n go?
I had it accidentally when I shifted things. It was in the wrong place, and I was like, "Where did it go?"
I was just making sure
It's
I
supposed to
got it
be
down.
up there.
I saw it too.
I think you wrote it probably originally. It's just when I started shifting things around that I apparently didn't drag my circle big enough. Yeah. Okay, so it's going to feel very much like what we did when we were finding Taylor polynomials. We're going to find many derivatives. We're going to evaluate them. We're going to simplify things, and we're going to try to condense the expression so that it looks like a more compact form, just like we were doing in the last section. So there are guidelines. We're going to write them out. So these are guidelines for finding Taylor series. So the first thing to do is to differentiate f of x several times. And evaluate at c. So you're going to find f of c and f prime of c and f double prime of c, and you're looking to find enough of them that you can see a pattern. So there's really not a like always find 5 kind of thing. Like 3 might be enough and it might not, so you're just going to do it until you see a pattern of what's going on. The second thing that we're going to do is we're going to use the sequence developed I should say to form Taylor coefficients. Right, and those Taylor coefficients are the a sub n's, right? So a sub n is the nth derivative at c over n factorial. And we need to determine, just like before, the interval of convergence. And the last thing is to put the sequence together and simplify it as if possible. Okay, so we're going to do an example. I think I've got enough space on this page to do it, or if not, I'll shrink what I've already written. So we're going to use the definition of Taylor series to find the Taylor series centered at C. And if C is equal to 0, we call it a Maclaurin series, but it's still a Taylor series centered at 0, so it's a special case. You got it. So our example that we're going to do is f of x equals e to the 2x. And we are going to do a c equals 0 one, so we're going to center it at 0. That didn't work. Let's try one more time. Here. Okay, so we're going to do several derivatives. That's the step one, right? We're going to try and find several derivatives. Sorry, those look like they're running into each other. Maybe if I put a line between them, it'll help a little bit. So we're going to do the, we're going to do the values, and we're actually going to evaluate them as well. So find the derivatives and evaluate. So we're evaluating at f of 0. So actually, let me write it this way. Our f of x, of course, is e to the 2x. And then we'll do it kind of like when we did Taylor polynomials, f of 0. So what is f of 0? It is 1. All right, let's do some derivatives. So what's the derivative of e to the 2x? 2 e to the 2x. And if we evaluate that derivative at 0, what will we get? 2. How about a second derivative? 4 e to the 2x. And evaluated at 0, we get 4. We'll do a couple more. The third derivative of x, 8 e to the 2x. And evaluated at 0 gives me 8. You can probably do the next one without even taking the derivative because you have an expectation already of what is happening with this pattern. But the derivative is 16 e to the 2x. And the fourth derivative at 0 would then be 16. Okay, so take a look at those numbers. 1, 2, 4, 8, 16. They're what? They're multiplying by 2. And so what kind of a sequence do you know multiplies by 2 as it goes like that?
Powers of 2.
Powers of 2, right? It's a geometric sequence. It's powers of 2. So these are 2 to some power. So all of this is happening as 2 to some power n. Maybe it starts at n, maybe it starts at n minus 1. We can shift it to make that work at the very end. That's not the point. But it's powers of 2. Yeah, for sure. So when we're taking a look at writing this series out, it starts out with 1, and then it was 2 times x to be x minus c, but c is 0. And then we have 4 over 2 factorial, and it's x squared. And then we have 8 over 3 factorial, and it's x cubed. All the way out to eventually it's 2 times x to the n over n factorial. And it keeps going, right? Like that doesn't end there because the values go to infinity. So let me put that dot, dot, dot at the end just a second. Okay, is that all right? Cool. So this is the summation from n equals 0 to infinity. And it's that piece that we have at the end. It's the 2 to the x to the n, 2x to the n, over n factorial. Or if you would prefer, you're welcome to write it as 2 to the n, x to the n. That would be okay. They don't necessarily have to have the same starting spot. But we want to make sure that we actually get the first term. So if n is equal to 0, what will that give me on top?
1.
It will give me 1. And what will it give me on bottom?
1.
1. So I get the number 1, which is my first term, right? And if you want to double check to do just one more to make sure we didn't get off by our pattern somewhere along the way, you can test any other of them. Let's do n equal to 2. So this was n equal to 0. N equal to 2 should be this one. Let's just make sure it works. So if I have 2 to 2x squared, do I get the 4 on top? I do, and have the x squared to the side. And do I get 2 factorial on bottom? Yeah. So this is the pattern that we were looking for. This is my Taylor series, or more specifically my Maclaurin series, since I've got c equal to 0. Okay? So this is only an example I'm going to do of this type, because they all work this way, and we've done Taylor polynomials already, right, and Maclaurin polynomials, and so we've seen this process happen again and again. So we're familiar with this as a general pattern, just not with the dot, 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 right, and the infinity business. There's one other thing in this section that's going to come up, and it has to do with, I think I've got it on the next slide, I do. It has to do with using this table that's in your book. This is a picture of it. It's not a great picture, but I'll leave it up as we're doing group work if you need to reference it, or you can pull it out of your paper, of your book. This is actually on page 674. So going ahead, you'll have this page for your test. Okay, I will give you page 674, so it's not like something you're going to memorize or anything like that. But the idea is to use something in table form and then be able to create series from those tables. So this almost kind of feels like when you did integration in chapter 8, I think it is, in Calc 2, and you had integration using tables. Well, you got to provide the tables, otherwise you can't do them, right? It's the same idea. So we're going to use this table form to create other series, and I'm going to show you an example of one using the one that we just did. So we used the function e to the x, right? E to the 2x, excuse me, right? And you'll see right here there is an e to the x in this table. And we can actually use that expression all expanded out from that point, from the table point, as well as the way we just did it before. It's another method for doing this particular function. So we're going to do, I'll flip my screen so I can give you some directions, but that's the table we're going to be using. So this is going to be use the table of power series. For elementary functions, to find the Maclaurin series. And if you look back over here, these are Maclaurin series the way that they're written out because they're all centered at 0. So that's why that's showing up there instead of the word Taylor series. Okay? So at the end, you can see some different things that are happening. But all of the functions themselves from the top to almost the bottom, we have Maclaurin series. Okay, so we're going to use that same one that we just did, but we're going to do it in a different way with these directions now. So just pay attention to which direction set you're in as to know which ones you're supposed to be doing. And I'm going to just write down what the e to the x was supposed to be. So e to the x on the previous slide from the table says that I have 1 plus x squared over 2 factorial plus x cubed over 3 factorial, and it continues indefinitely. That's what the table said. So we take what the table says, and then in place of our x, we actually have 2x. So we replace all the x's with 2x. So if I do that, and now I have e to the 2x, I have 1 plus 2x, it's a terrible parenthesis, plus 2x quantity squared over 2 factorial, 2x quantity cubed over 3 factorial, out indefinitely, right? Just replacing them. And we got to the exact same place we did using derivatives on the previous type of problem solving. So this ends up equaling the same thing we had before, summation from n equals 0 to infinity of 2x to the n over n factorial. And we did it by using tables. Now, this sort of harkens back to what happens in Calc 2 as well, right? Like there were tables that were in the table section that allowed you to maybe not have to do integration by parts because it's a very specific example for very specific functions, right? And so when Dr. Drake taught the class, which I know he had at least a couple of you, and I don't know how many of you, but when he taught that class, when he gave the test for using the tables, he didn't give you all the tables, did he?
No.
He only gave you some of them because he didn't want you using the things that were in the table for other methods that you already had methods to use them for. So just keep that in mind that there's going to be questions that are going to specifically ask you to use the table. Definitely use the table for those. But if it asks you to do it like we did over here, right, using this definition, these are the directions here. Use the definition of Taylor series that you're using the definition of Taylor series. All right? Okay, let me do the homework part, and you guys can get on the boards. Yeah, lots of time today. Okay, so we're on page 677, and it's numbers 6, 9, 12, 14, 30, 31, and 36. It's not very long. And on Wednesday, we will be reviewing in class, so come prepared for that. Friday. Today's Wednesday. Sorry. This week has been so off for me. I'm sorry. It's just been a weird week for me. I've had so many appointments with my kids in different places and stuff, and
It's been a long week.
I don't know. It has been. It has.
Who knows
Alright.
that Monday
Wait.
is Wednesday?
I'm just off on all my days.
It's on that. Okay.
All right, and I have I seen everybody at this point come in for a gateway at least to try and start the process? I think I have.
Have you seen Don,
Sue.
remember?
I think that I've seen Aaron. I can't remember
I
now.
don't think I'll be able to come in for Android or the Zoom.
Okay, that's okay. So do keep in mind that if you're not quite finished, and some of you are finished with some or part of the different things, so Jubal was asking me, is it really worth it to keep coming in if I get a score that I'm okay with? It's up to you, right? It's your choice. But if you want to see what that score gets you in terms of the points, it's not just like, oh, I got 7 out of 10 of it is a 70%. It doesn't work like that. But you can see inside of the syllabus what it actually is, and you can decide to make your decision from there. But you can take each of them up to 4 times to get the 100% full credit if that's what you choose to do. I will be in my office right after this class, and then I actually am leaving campus at 2 today. I have an appointment. I told you these appointments are crazy. And then I'll be back tomorrow. So if you need anything from me, let me know. And just like Hannah did today, if you need to come in at a different time and it's not my office hour time, let me know, and I can probably find some other math professor that's around and that you can do it with them or give it to them when you're done. So we can make that happen too, okay? All right, take a look at this homework set.